Today I want to talk about tangent space. Remember, we're moving towards Lie algebras now, so we're going to find that if you start with an algebraic group and you take the tangent space at the identity element, that gives you a vector space which has a canonical structure of Lie algebra on it. So, but before we do it in general for an algebraic group, let's just start off at the level of affine varieties and review the notion of tangent space in that setting. So let X be an affine variety and take some point little x in X. So I want to discuss how to construct this vector space Tx of x, which is the tangent space to the variety big X at little x. So I want to kind of motivate this a little bit, and so kind of make it look like tangent space as you would kind of naively come up with the definition. So for that, you've got to start with a closed embedding into affine space. In other words, that you're given coordinates. So X is sitting inside affine n space, I'm given closed embedding. And as we've discussed, that's equivalent to realizing the coordinate algebra of X as a quotient of the polynomial algebra in n variables. So I here would be just the ideal of X, the functions in the polynomial algebra vanishing on that subset X. And let's assume that that ideal is we've got some given generators. It's finitely generated, F1 through Fs, going to generate the ideal of S. And then I want to take a line, L, in at affine n space. That's just k to the n, that's just a vector space. Take a line passing through the point X. Okay, so this point X is given inside there. So of course that line, I can write that as a vector equation. It looks like X plus parameter vector for t in the field and some vector v. So we're in a to the n, so v is just an n tuple in k to the n. Okay, so that's kind of the vector in the direction of that line. And then the intersection of that line with our closed subspace X, it's just all the points such that, well, the X is cut out by the vanishing of those functions, the F's. So we want Fi on X plus TV to equal 0 for all I 1 through S. So I'm going to call L a tangent line to the closed subset X at the point X. If so I guess I should have noted that for these equations, t equals 0 is definitely a solution to these equations for all I, because the point little x is inside big X. So I'm going to call this a tangent line if t equals 0 isn't just a solution of those equations, but if it's actually a multiple root of these equations. So that's the definition of tangent line, and I'll call the vector v, the direction vector for that line, I'll call that a tangent vector. And then the idea is that the tangent space, Tx of x, is going to just be the set of all tangent vectors, v in Kn. So I think this is not bad, but I should probably spell out exactly what we mean by multiple root here. So how can we give a proper meaning to what multiple root means? So to do that, we're going to look at the algebraic linear map, this partial differentiation with respect to ti, but we're just on the polynomial algebra, so this is just a simple algebraic notion. So I want to look at the Taylor expansion of the function fi, right? So fi, that's a function from k to the n to k at the point x. And so that Taylor expansion, it tells you what fi of x plus tv looks like. And so it's fi of x, which is just 0. And then the linear term is t, and it's going to be, so it's going to be this partial derivative dfi by t dtj evaluated at x times vj, summing from j equals 1 to n vj. So that's the linear term. And then there'll be a quadratic term and so on. And so now it's kind of clear that saying t equals 0 is a multiple root just means that the linear term so that linear term right there should be 0 for all I. So, in other words, that vector v is in the tangent space. It's a tangent vector if and only if those that t coefficient dfi by dtj of x vj is 0 for all I ranging from 1 up to s. So those are the equations that cut out this tangent space. In other words, tx of x is, so it's all about this matrix, partial dfi by dtj of x. So that's, let me see, I is running from 1 up to s, and j is running from 1 up to n. So that's an s by n matrix. So it's a linear map, and the tangent space, just by definition, is the kernel of that linear map. So from that you see that the tangent space is a subspace of the n-dimensional vector space k to the n, which was our affine space that we started with. Okay, so that's our provisional definition. Of tangent space. I'm going to massage this definition a little bit to make it a little bit more coordinate free in a second. But already from this you can do some examples. For example, if x is the whole affine space, well then there are no equations cutting out s. This s is just 0, so this is kind of a degenerate case, but it's still worth pointing out that in that case the tangent space is just the whole of k to the n. Let's do another easy example. Let's say x is the unit circle. Right, so there it is the unit circle. So what's that? That's the vanishing set of t1 squared plus t2 squared minus 1 sitting inside affine 2 space. So what's this matrix in that case? So there's just one polynomial equation now, so s is 1. So this is just a 1 by 2 matrix, and the first entry I've got to differentiate that with respect to t1, so I get 2t1, and then evaluate on x, so I get 2x1, right? This x is just at some point inside x. So that's the first entry, and similarly the second entry is 2x2, and so the tangent space is just the kernel of that matrix. So it's the span of, I guess, how do I get into that? I need what to do? I do x2 minus x1. that would do the job, right? So x is some point on the unit circle there, and so there's the vector x, and yes, indeed, this is a vector orthogonal to there, and so that vector spans the tangent space, and I guess you see what I've done. The tangent space, I've kind of shifted the origin, so I'm treating so that the tangent space is a subspace. I've shifted the origin in my definition, so the tangent space is spanned by that line, but with the origin being shifted to x. Oh, that's true, providing P is not 2. But if P is 2, something's gone wrong here, right? In characteristic 2, that's just the 0 matrix, and so the kernel of that matrix is the whole of affine 2, it's the whole of the vector space K2, which is not right, is it? So what's gone wrong in P equals 2? Well, in P equals 2, this polynomial that I wrote down is actually T1 plus T2 plus 1 squared, and so I actually took the wrong f here, because you've got to take the f's that generate the ideal of x, and in this case, the f I wrote down, it doesn't generate the radical ideal. You have to square root it. So if I did it again in characteristic 2, I would use this f, and then again I would find that again the tangent space is one-dimensional, and it would have worked out. But we're never really going to worry about positive characteristic pretty soon. But it shows that my definition is robust enough. Okay, so that's our provisional definition of tangent space. Now we've got to work on it a little bit to see if we can go coordinate free. So let's just have a little bit of language, I think is useful. So I'm going to call a linear map from the coordinate algebra of x to x, so a linear map. It's a derivation. If it satisfies Leibniz. You all know what I mean, Leibniz. So applying d to a product is d of f times g plus f d of g. I'm just saying this for the K algebra K of x, but of course you can take the definition of derivation makes sense for any algebra. Okay, so maybe it's worth noting that the derivation, for example, the identity element in this algebra necessarily goes to 0 under a derivation. Just use the 1 equals 1 times 1 and apply Leibniz. That's how you see that. I'm going to write the K of x for the vector space of all such derivations. As I said, I could just as well replace K of x here by any associative K algebra I like. Indeed, you don't even need it to be associative in general. So this is a subspace of the vector space of all linear maps from K of x to K of x. And of course, this guy here is an associative algebra under composition. And we talked back right at the very beginning, we talked about how any associative algebra could be made into a Lie algebra by defining the Lie bracket to be the commutator. And then it's called, not end, but you use GL, K of x. It's the general linear Lie algebra on that vector space. So the point is that this space of derivations, it's not an associative subalgebra. It doesn't even contain the identity element, right? Because a derivation sends 1 to 0. However, it is a Lie subalgebra. So this is, I think, really the reason why Lie algebras come up so often. Whenever you're thinking about derivations of some vector space or of some algebra, derivations of some algebra, that always gives you a Lie subalgebra of the general linear Lie algebra on the underlying vector space. So this is something you should check. It's easy, but you have to take two derivations and you have to check that their commutator is again a derivation. So it's kind of the most important place is where Lie algebras are going to come from. The commutator d1, d2 of two derivations is a derivation. So that's kind of the very important point. Okay, great. So let's now be a little. So far, everything I said, I didn't need k of x. It could have been any algebra at all. But now let's use this given point that we've got inside affine space. I'm going to let k sub x be k of x over mx. So mx here, that's the maximal ideal, so kernel of evaluation at x, the maximal ideal of the coordinate algebra of x corresponding to the point little x. And then I'm going to let the k of x, kx, be the set of all linear maps from the coordinate algebra to this kx. This kx is just a copy of the field k, right? We're quotienting out a maximal ideal, so that's the field. But I want to keep this little subscript x to remind you that just to keep that point x in the notation. So this is going to be all linear maps with the property that d bar of a product is d bar f g evaluated at x plus f evaluated at x d bar of g. Okay, so these evaluations f of x and g of x, they're just scalars, so I'm just scaling in there. Okay, great. So I'm going to give this a name. This is called the vector space of point derivations. For the point x. So this notation, this k sub x notation, it reminds you that the point x is involved. So this axiom here for a point derivation is kind of like Leibniz, but you evaluate one of the functions at x in that expression. And so because this is so like the definition of derivation, I think it's kind of clear that if d is a derivation, then if you define d bar just to be d composed with evaluation at x, that is a point derivation. Okay, so I've got this Lie algebra of all derivations of k of x. And for any d in there, if you compose that d with evaluation at x, you get this d bar. That's kind of an important formula right there. And then d bar satisfies this modified version of the Leibniz rule. This is the formula for a point derivation. So this d bar becomes something in this vector space of point derivations. It's just a vector space now. This doesn't have any kind of Lie algebra structure or anything on it, having evaluated. Okay, so let's think about what these point derivations are. Let's start with the whole polynomial algebra. And see if we can understand what this vector space of point derivations on the polynomial algebra is. So let me see. You can take Kn, so if you take some vector in there, the V that we had before. So that's some n tuple. You can build out of that a point derivation. Well, you can build out of that V, you can build a derivation, right? Each of these partial derivatives, d by dtj, that's a derivation of the polynomial algebra. So if you take a linear combination of them, where the vj's, the entries of this vector v, are the coefficients, that's a derivation. And if you just compose it by evaluation at x, then that gives you a point derivation. So this guy right here, let's put a box around that guy, because that's going to be important. I'm going to call that, I guess I would call this thing here, I would call it d sub v, and then when you compose with evaluation, it becomes d sub v bar. So any vector in the vector space k to the n gives us this point derivation dv bar for the point x. So it's just this partial derivative, and then you evaluate at x. In fact, this is an isomorphism. So this linear map that I've just defined, sending v to dv bar, is actually a linear isomorphism between these two vector spaces. So how do you see this? I'm not going to write out the full details, but it's kind of easy. Any point derivation for the point x is equal to dv bar, where v is the point defined by setting vj to be whatever the point derivation does to tj. So the point is that because of this Leibniz rule, a point derivation, it's uniquely determined by what it does to the tj's, because they're algebra generators. So just from knowing these vj's, that uniquely determines any given derivation. And this dv bar, defined from these vj's, this dv bar has the same value at tj as d bar does by this definition. And so you see that any d bar is equal to a dv bar for this for the vector v obtained just by evaluating at the polynomial generators. And so now you just easily see that the map sending d bar to v for v defined in this way is a two-sided inverse. So this is kind of easy. Okay, so at the heart of the argument is this observation that a point derivation is uniquely determined by what it does to the tj's because it satisfies this modified Leibniz rule. Okay, great. Now earlier, in our provisional definition of tangent space, we showed that the tangent space of big X at little x was the set of all vectors in Kn, that's the tangent space of the whole of affine n space, such that dv bar fi is 0 for I equals 1 up to s. So that was exactly, I've got this new notation for this expression dv bar, but that was exactly our provisional definition of tangent space. It was exactly the vectors satisfying that equation. That's exactly saying that dv bar kills all of the fi's. I could write this just maybe a little bit better, avoid choosing the generators for that ideal. That's just exactly the same as dv bar sending the ideal of x to 0. Because, well, if dv bar kills all the fi's, using the point derivation rule, this modified Leibniz, it's easy to see that dv bar must actually kill everything in the ideal that those f's generates. So that's a little bit better already, right? We've got a description now of tangent space which doesn't involve picking generators for that ideal. Okay, so we had this isomorphism up there that was called dagger. So if I apply dagger to this, you see that that an isomorphic copy of that vector space, I can describe it as the so dagger sends the v's in Kn to point derivations at the point x, and then point derivations which kill I of x. Right, so I'm just sending the v's in the first set to the dv bars. So that's just the same, well, an isomorphic copy of this same vector space. And this, so what have we got? We're looking at functions from the polynomial algebra to the field which kill the subspace of the polynomial algebra that's the ideal of x. And that's just exactly the same as functions. I don't even need to write a set. It's just exactly the point derivations from k of x to kx. Because, I mean, if you've got one of these d bars up here, k of x is a quotient of the polynomial algebra. If d bar kills I of x, it factors through the quotient, and that d bar induces an element downstairs. And conversely, if you have a point derivation downstairs, you can just pull it back through the surjective map from the polynomial algebra to k of x to get a d bar upstairs which kills I of x, right? So that's just the kind of usual obvious isomorphism, because k of x is a quotient of the polynomial algebra. And so this guy right here that we've ended up with, what we've just shown is that this is our tx of x up to this isomorphism. And in fact, what I now want to do, so this kind of motivates this as being the important space. I want to get rid of our provisional definition, that vector space in our provisional definition. We've now proved is isomorphic to this new vector space of point derivations. And that's the right definition that I actually want to take as the main definition. So let's now start again after all of that motivation. So we've got x an affine variety and a point little x in x. I'm going to define the tangent space to x at x is the vector space Tx of x, which by definition is the vector space of point derivations from the coordinate algebra to the field. Point derivations for the point x. Why is this better than the provisional definition I had? Well, you see, it's now coordinate free. This doesn't mention this closed embedding into affine n space at all. So this is definitely preferable because it's coordinate free. Another reason it's better, well, it's actually kind of functorial. If you have a morphism from x to y of two affine varieties, and say that takes point little x in x to point little y in y, then you get a linear map between the tangent spaces called d phi x from tx of x to tx of y. So this is called the differential of phi at x. And how's this defined? So I've got to tell you what this differential takes a point derivation on the coordinate algebra of x to, it's going to take it to the different d phi x of d bar, where, so I've got to define this thing. It's meant to be a point derivation on the coordinate algebra of y. So I've got to tell you how to plug in any element of the coordinate algebra of y to this. And so now what can you do? How can you get an element of the field out of this? Well, you can do the comorphism phi star to f. That gives you an element of the coordinate algebra of x, because this comorphism, it's an algebra homomorphism in the other direction. And then I can apply the original point derivation on the coordinate algebra of x to that. So that's the definition. It's obviously a linear map. But I guess we should check just a little bit. Why is this a point derivation? From k of y to ky. So maybe I should do a little bit of that. So I've got to check the modified Leibniz, right? So I've got to check that if I take an f and a g, so instead of f there, I'm going to take fg. So I'm taking fg, a product of two functions on y. So I've got to look at d bar phi star of a product. But that's d bar phi star f times phi star g, because the comorphism is an algebra homomorphism. And now I can use that d bar was a point derivation for the point x. And so I'm going to get what phi star f of x d bar phi star g. And so this is what I want, right? This d bar phi star f, that's just our definition of this new derivation applied to f. And phi star g of x, because of the definition of comorphism, that's just the same as g of phi of x, which is g of y. And similarly, that's f of y d bar phi star g. And that's the silly check that this new guy, d phi of d bar, is a point derivation from k of y to y. Okay, so that's good. If you have a morphism of varieties, you can differentiate and you get this differential between the tangent spaces. We should observe that if you've got three varieties, and you've got a morphism phi and a morphism theta taking maybe x to y to z, we should check. So then you can do the composite, right? Theta after phi, and you can take its differential at the point x. So that goes from the tangent space to big X at little x to the tangent space to big Z at little z. So of course, this would better be equal to the differential of phi at x. Phi, okay. This would better be the differential of phi at x compared with the differential of theta at y. So this is kind of a chain rule. And that's very easy to check. You just have to plug into the definitions, and it just follows because the comorphism theta after phi star is phi star after theta star. In fact, passing to tangent space, or taking differential on objects or morphisms, is a functor. That's what this checks from. I guess it's from pointed affine varieties to vector spaces. So now we see that things are looking smelling just right, and we've now got a nice notion of passing to a tangent space at a point, and everything's kind of fitting together just as we would expect. So let's make a few other observations about this construction. I'm not going to prove everything now, but let me see. What about products? I mean, we should just sort of understand tangent space in all of our usual constructions in affine algebraic geometry. So if you have two varieties x and y and you have a point in their Cartesian product, what do you expect the tangent space to be? I'm just going to write equals. You can ponder exactly what I mean by equals there. Of course, that should be the tangent space to x, direct sum the tangent space to y. So tangent space does what you would expect on products. Let me see, what else should I talk about? What about if you have a closed embedding? Well, then you can look at the differential. So I need a point. The differential of phi at some point that goes from the tangent space of z at z to the tangent space of x at z. This is actually an isomorphism onto its image. And the image of this differential, it's exactly all the elements of the tangent space of x which kill the ideal of z. Let me just give myself a tiny bit more room there. Right, so the tangent space of x at z, this is point derivations from k of x to kx. And so it's all point derivations on the coordinate algebra of x which kill the ideal of z. And indeed, this is just exactly, we just saw exactly this. When I was motivating the definition of tangent space, we were looking at the closed embedding of x into affine n space, and I exactly wrote that set down in that special case, and in general it's exactly the same argument. So the tangent space of a closed subset of x, it's canonically identified with this subspace of the tangent space of x by the differential of the closed embedding. It's exactly the subspace consisting of all the elements of the tangent space of x which send the ideal of the subset z to 0. So that just naturally upgrades our motivating example that we did at the beginning. So that's closed subsets. What about principal open subsets? So if you have some f in the coordinate algebra of x, and you have some point in the principal open subset. So remember, that means that f of x is non-zero. Well, now this principal open subset, we've discussed how that's an affine variety, and the inclusion of that principal open subset into x is a morphism for the variety structures. Its differential is actually an isomorphism. So this is what dix from the tangent space at x for this principal open subvariety with its affine variety structure, and the tangent space to actually x itself. So this should kind of be intuitively obvious for you. The tangent space at a point, you should only depend on an open neighborhood of that point. And that's what the tangent space, it kind of only sees a neighborhood of x. It's a local thing passing to tangent space. So that's exactly what this statement captures for you. So how would you see this? Let's see. The coordinate algebra of this principal open subset, remember by definition, that was the coordinate algebra of X localized at F. And so the comorphism I star is just the inclusion of the coordinate algebra of X into that localization. So what we have with this map, this differential, is the map from point derivations from the localization to Kx to point derivations on X. And this is just the natural restriction along, well, the comorphism I star is just this algebra homomorphism from K of X to K of X F. Okay, so that's exactly what our differential dIx is. And to show it's an isomorphism, we need to show that any d bar in the right-hand space kind of lifts to something on the localization. So I'm not going to go through everything here, but the issue is to define. So you're kind of trying to extend this point derivation to, you know what it is on elements of K of X, and you need to extend it to fractions, so things like G over F. And I mean, there's kind of no choice here what to do, right? You know what d bar of G is, and you know what d bar of F is, and you're looking for what d bar of G over F is. So there's kind of no choice in what you do, and it shouldn't be any surprise that this is, of course, it's just the quotient rule. So what is it? It's the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared, and it makes sense. So that's the unique thing that you have to do, and it makes sense as f of x is not 0. So that's just sort of a little bit of hint how you see this last fact that I've written down. Good. So let me just maybe finish with just a couple of beginning examples. So we're going to practice I'm teaching you how to differentiate. So we're going to practice this next time, and we'll calculate quite a lot of these. But maybe first example, we should think about the tangent space to the general linear group, GLN, and there's a distinguished point around, namely the identity. But by definition, the general linear group is a principal open subset of the variety of all n by n matrices. So the fact that I just showed, it's just the same as the tangent space to the vector space, the full affine space of matrices. And we saw already that for a full affine space, for a vector space viewed as an affine variety, the tangent space was just the same underlying vector space. It's kind of useful to really understand this. So this is the IJ matrix unit, EIJ. That's the basis, linear basis for the vector space of n by n matrices. So this is this linear basis. Whereas this definition of tangent space, now we're using this coordinate-free definition. This is point derivations on the coordinate algebra, this polynomial algebra, for the point E, the identity matrix. And so I just want to spell out exactly what the IJ matrix unit corresponds to. So it's exactly partial differentiation d by dt ij. Remember, the coordinate algebra of n by n matrices is the polynomial algebra in n squared indeterminates. So EIJ, the IJ matrix unit, corresponds to partial d dt ij followed by evaluation at E. And so this guy is a point derivation from the coordinate algebra of matrices. Golly, it takes a lot of space to write that, doesn't it? There we go. To the field, that quotient by that maximal ideal for the point E. What about the tangent space of maybe SLN of K? So that's a closed subvariety of GLN of K. It's the vanishing of determinant -1 inside GLN. So its tangent space should be a subspace of matrices. It should be all the points in the tangent space of GLN, which we've just identified with n by n matrices, such that dv bar. You see, you can see how I just do this without even really thinking. I'm identifying this tangent space. I really wrote equals here. This happens all the time. Instead of thinking about the tangent space in this kind of annoying way for a full affine space as point derivations, I'm just going to identify it. So right there. So this is common practice. I'm just going to identify that tangent space, which by definition now is point derivations. I'm just going to identify it with the underlying vector space. So that's this isomorphism, sending vector v to this point derivation dv bar. So we want so it's cut out by these equations, right? Determinant it's got to kill the polynomial that generates that ideal, determinant -1. I wrote v here, but really it's matrices, isn't it? A equals aij, 1 less or equal to ij less or equal to n. I shouldn't write v, it's just matrices. So it's all matrices A in the matrix vector space Mn of K, such that, so I'm just translating all of this, we want the, so of course that matrix is the sum of the aij's times the ij matrix units, and the ij matrix unit corresponds to this d by dt ij, and we want it to kill determinant -1 when you evaluate at E. So that looks kind of gruesome and nasty, which is fair. Let's just do SL2. It's really not too bad. For SL2, determinant is just T11 T22 minus T12 T21 minus 1. We want to partial dt ij and then evaluate at the identity matrix. We want that to be 0. But you see, the identity matrix is zeros off the diagonal. So this stuff here, even when we've done some differentiating, we're either going to have a T12 or a T21 left. But when you evaluate that on the identity matrix, you get 0. This is a constant, so it goes straight away. So we're only going to get stuff from doing partial derivatives of this kind of diagonal product, the product down the diagonal of our matrix. And that's only going to give us stuff when I and j are either both 1 or when they're both 2. So we're only going to get A11 dt11, which is what, T22, and A22 T11 of E, which is just A11 plus A22, because these are just evaluating on the identity matrix. Those are both 1. So what have we got? It's 2 by 2 matrices of trace 0. This right here, that's just the trace of the matrix A. And I just did SL2 because it was easy, but if you think about the definition of determinant in general, it's exactly the same picture. This tangent space for the closed subvariety SLN of k inside GLN of k, it's all A in Mn of k, such that trace of A is 0. So the tangent space to SLN at the identity, it's the closed subspace of the tangent space of GLN corresponding to all the matrices of trace 0. Okay, I think I'm going to just stop there. But what we've got to do is we've got to give this tangent. So we're interested in algebraic groups, and we're always going to look at the tangent space to the algebraic group G at the identity. And so far that's just defined as a vector space. The next thing we've got to do is actually give that a structure of a Lie algebra in its own right. And so we'll see that any algebraic group passing to this special tangent space will give us a Lie algebra. And so that's this process of linearizing algebraic groups.